Hi, this is Venkatesh Prabhu. We'll be discussing the simulation studies in a process batch reactor using Berkeley Gordon. Here, I already mentioned that there are four conditions. Is there first condition is the inbuilt condition, which is going to be method, that is range put of fourth order method. Start time is 0, stop time is 10 minutes, and the differential time is 0.02. This is going to be changeable based on our conditions. We can change the conditions. The next one is the arrivable conditions we need to give. For a batch reactor, I just have equations already. Let us see this directly. This is the model for a batch reactor. Yes, first condition is going to be the inbuilt condition. The next is going to be the differential equations. These differential equations changes in the biomass, changes in the substrate, changes in the product. So changes in biomass is d by dt of x is mu into x. Substrate is 1 by y minus 1 by y mu into x. dp by dt is equal to beta into x. Beta is the constant which is going to be the coefficients for the product formations. So once if we are given a differential equation here, then whatever the differential x, s, and p, we need to assume the initial values as x equal to 0.1, where whatever it is, biomass, then substrate is 50, product is. So after feeding these, the constant values, which is going to be the multiplication factors like mu, then 1 by y, yield coefficient, beta values, all the values must be assigned. Once all the values were assigned, then we will go to the stop time as 100 and start time as 0. The differential time is 0.02. Well, giving the run conditions, we will get the conditions of x, s, and p. Its legend values are x is going to be a constant biomass is going to be formed. Substrate it is reduced drastically at 20 before 20th hour, and product is steady increase. Suppose if I want to check the conditions, the differential time I can make it as the stop time as 20. 20, then we'll run it. We'll see how. So this is the way we can able to predict the first order batch reactors, that is for batch reactor operation. The substrate is reducing, product is increasing, as well as biomass is also increasing for the time period of 20 hours. So if you want to do the experiments, and these predicted results will be fit with the experimental results and find out the changes in the thing, or it would be compared with the experimental results, predicted results. Similarly, we will also try for the uh, continuous system. So for continuous system, already the receptivity model is there. It's a chemostat model. So, so all these four lines are built-in conditions. Method or K4, which is going to be the default values. Then start time is 0, stop time is 50, differential time. Now X is mu minus D. This is the theoretical models. Already it is there in the book. So we will form a two differential equation. One is for X, another is for S. For both x and s, we need to give the initial conditions. Then mu is equal to mu max s whole divided by ks plus s. The dilution rate is given it as d equal to 0.1 and the initial substrate is 10. The mu max value is also given the ks and the yield coefficients. After feeding all the values, we can run the program. So we will be getting the results. That is, there are only two differential equations x and s. Based on x and s, we will be getting the model like this. Suppose here also you will change the time and check the time within 10 minutes, 30, within 15 hours. What is the changes in the system? So we'll find out the maximum biomass which is going to be attained at 12 hours. I'll change it as 12 hours, then run it. So you will be getting the results like this. And the tabulated value can be extracted, the legends can be substituted, and the initial conditions can also be added. Similarly, we'll also try for a fed batch reactor. For fed batch reactor, the model, go to the new model, then again fed batch is the initial volume is it is a variable volume system. Since it is a variable volume system, and there are three differential equations. One is x, another one is s, another one is v. Volume from initial volume, it is going to be raised, that is dv by dt. Volume is going to be raised based on the flow rate. So uh, x, s, and v. There are three lines we will be getting for that. X is equal to d by dt of x is mu into x. ds by dt is equal to f by v into s naught minus s. So these two equations which is going to be available in the textbooks of bioprocess engineering like Schuler and Fergie or Bailey and Wallis, anything. Then the flow rate f is equal to dv by dt. The initial conditions for all the three differential equations were given and the constant were also be given. When you run the system, you will be getting the results. With this, we can able to expect or predict how long we can able to operate the reactor, whether it is going to be between 15 hours or it can be extended to 100 hours or more than. So, for example, 100 hours when we are going, stop time is 100. So, only the x is going to be increased. The rest, there is no changes in the substrate and the v. There are small changes in the v. Further, 100 is going to be 1000. So this is beyond the limit. So we should not run it for 2000 hours. So 10 hours if you run it, what is the changes? Or 25 hours, 1 day. So the 1 day if you operate the full batch reactor, that will be good for the complete substrate reduction, biomass formation. Those where volume is not going to be changed drastically. It is going to be from 1 to around something nearby 2.5. So this is the way we need to check the simulation studies in a batch, full batch or continuous system. Let's just try another example for a immobilized system, immobilized animal cell. immobilization of animal cells. In this, so this is the way we will get the results for the mobilization. Again, there are three differential equations. One is biomass, another one is substrate, another one is product. The differential model, that is the dynamic models for biomass, substrate, and product is given, and its initial values were also be given. The differential time is 0 to 200. For this is the expected results, legends, then initial conditions. You can see how the substrate is reducing, how the product is increasing, as well as biomass is increasing. Thank you.